Bring acceleration of an object near Earth's surface. So all objects that are near Earth are going to experience acceleration due to gravity whenever they're let to free fall. Okay, so the acceleration due to gravity, we actually use it quite frequently, so they actually give it their own symbol of G. Okay, but it is an acceleration, so A or G would be the variable for this. Okay, so for Earth, the average gravitational acceleration is 9.8 meters per second squared. So whenever we're writing that as a vector, it would be 9.8 meters per second squared down, okay, or we can use negative 9.8 meters per second squared, okay, if down is defined, or if, yeah, down is defined as the negative direction, okay. So this can't be used for other planets. They would have their own gravitational constant. This is just for Earth. So this value is true for any object of any mass if it's not experiencing air resistance. So for the purpose of this class, we're not going to consider air resistance, at least not at this time, just because then it would complicate things. So we're just going to assume that all things are falling in a vacuum. Okay, so for example 1, a cat knocks a flower pot off a ledge. The flower pot hits the ground 2.7 seconds later. How high above the ground is the ledge? Okay, so we're going to use the same methods that we did in order to solve the previous examples that we did with the kinematic equations. Okay, so I'm going to first start off by drawing a picture just to kind of get a better idea of what's going on. So I have a cat. Okay, and they're going to knock off a flower pot off a ledge. Okay, and this is what we want to know. We want to know how high above the ground is the ledge. They did tell us a time. Okay, so it took a total of 2.7 seconds. Okay, and we do know acceleration. Okay, because this is a free-falling object. We know that acceleration is going to be 9.8 meters per second squared down. Okay, and so we only have 3 variables, and so we do have to have 4 variables in order to solve for the missing one. Okay, so the only 2 other variables that we haven't used is v1 and v2. Okay, so for the final velocity, we don't know how fast the pot is going to be moving once it strikes the ground. Okay, but we do know what its starting velocity was because it wasn't thrown up into the air or thrown downwards, it was just knocked off. Okay, so its initial velocity would be 0 meters per second. Okay, so now we have 4 variables. We can set up our kinematic equation. And so we're going to use equation number 3, which is position equals initial velocity times time plus 1/2 acceleration times time squared. So plugging in the values, we got v1 was 0 times our time plus 1/2 acceleration, which is 9.8 times our time squared. Okay, so whenever we put this in the calculator and calculate it out, we should get 35.721 meters. Okay, so the flower pot was almost 37 or 36 meters above the ground. Okay, moving on. So objects experience acceleration due to gravity even if their initial velocity is upward. So for example, if I have a ball and I'm tossing it into the air, as soon as the ball leaves my hand, it's experiencing acceleration of gravity, okay? Just because it's moving upwards doesn't mean that gravity isn't acting upon it, Okay, so if we were to graph this, okay, over time, we had our height, which would be kind of like our position versus time graphs, okay? The object would get thrown up into the air, and because of acceleration is negative, remember it's negative 9.8 meters per second squared is our acceleration due to gravity, okay? It's going to slow down till it gets to this peak top point, okay? So whatever height I throw it up to, it's going to continually slow down till it stops at its highest point, and then it's going to start falling back towards the ground and accelerate faster and faster in the negative direction. Okay, so this point up here at the top, the velocity is going to be 0. We'll just say meters per second, just so we have units. Okay, this is the highest point. Okay, and so on the left side of the graph, our velocity is going to be greater than 0, okay? Because it's going to have a positive velocity, but it's getting slower and slower and slower till it reaches 0. And then on the flip side, the velocity is going to be less than 0 because it's going to have a negative velocity and it's going to be changing direction, going back towards the ground. Okay? So, for example number 2, a tennis ball is tossed from your hand 1 meter above the ground with a velocity of 3.6 meters per second up. What is the maximum height above the ground? Okay, so we have a ball that's already 1 meter above the ground. So here's our ground. All right, and we want to know what is the maximum height. So the ball is going to be thrown upwards until it reaches a certain height. Okay, so we need to know what this height was. So this would be our change in position. Okay, so in order to find the maximum height above the ground, this is the key thing. It's asking us from the ground, what is its maximum height? We're going to have to add these two together. So we should have to find the maximum height. We would do delta D plus 1 meter. Okay? The ball is thrown upwards, so its initial velocity is going to be 3.6 meters per second up. We're just going to keep it positive as being the up signal. Okay. We don't have a time. We do have a final velocity though. If you think about it, if it's reaching its highest peak, just like from this graph, the highest point is going to be 0. So V2 is going to be 0 meters per second. And then we also know acceleration because gravity is working upon this object. So acceleration is going to be negative 9.8 meters per second squared. Okay? And then we're trying to find delta D. All right, so now we have 4 variables. We can use one of the kinematic equations in order to solve this problem. Okay, so we're going to use the equation final velocity squared equals initial velocity squared plus 2AD. Okay, so if I rearrange this equation so that it's solved for delta D, it would be V2 squared minus V1 squared all over 2A. Right, so if I plug in the things that I know, V2 was 0 minus Our V1 was 3.6 all over 2 times our acceleration. Right, and we should get that our change in position is 0.661 meters. Okay, but that's not our final answer because remember we're trying to find maximum height. Okay, so our maximum height, we're going to add 1 meter to this. So our height above ground, I'll put max height, is 1.66 meters. Okay. Another misconception is that the object has a final velocity of 0 as it hits the ground. Okay, so if you were laying on the floor and someone offered to drop a bowling ball in your chest, would you think that the bowling ball has a 0 velocity as it strikes the ground? Probably not. You probably wouldn't agree to that. Okay, so hitting the ground does stop the object, but the object is moving at a final velocity once it strikes the ground. Okay, so what is the tennis ball's velocity right before it hits the ground? All right, so if we look back at the problem, we're going to be going from this point here to the ground. Okay, so our position, our change in position is actually going to be -1 meter. Okay, because we started 1 meter above, so if the ground is going to be the ending point, we're going to be -1 meter from our starting position. Okay, our initial velocity is going to be the same, so our VI was 3.6 meters per second. Okay, our acceleration is going to be the same, of -9.8 meters per second squared. And we're wanting to know what is the ball's velocity right before it hits the ground. So we're wanting to know what is the final velocity. Okay, so here we have 4 variables. So now we can plug it into an equation. Okay, so we'll use the equation that we had before. So final velocity squared equals initial velocity squared plus 2AD. Okay, so plug in the numbers. Our V1 was 3.6 plus 2 times our gravity times our displacement. Okay, so then we should get that V2 squared equals 32.56. We would have meters squared over second squared. Right, so we would have to take the square root of both sides. We should get that the final velocity is plus or minus, if we're looking at it from the math standpoint, plus or minus 5.71 meters per second. Okay, so we would choose the downward one because that, if we think about the problem, it was, if it is going towards the ground and throwing up into the air was the positive velocity. Once it's going downwards towards the ground, that's going to be a negative velocity. So our final velocity is negative 5.71 meters per second, or you could have put 5.71 meters per second down.